Hi everyone, thank you so much for joining us today for a guest speaker session at Cohere for AI Regional Asia. We have with us Namgyu. Namgyu is a PhD student at KIST working on LLM inference efficiency. Today he will be talking about his research paper Block Transformers. Thank you so much for taking out your time and I'll hand it over to you.
Right. Thank you, Ahmad. Thanks for the invitation, and thank you everyone for joining. So again, I am Namgyu Ho from KAIST AI, and this block transformer work was part of a work done during an internship at LGI Research, thanks to their generous offering of resources and mentoring. So and this was presented at NeurIPS 2024. So let me get right into the paper. All right, so I want to outline the key takeaways of this talk. First, I want to give a very simple primer on the key bottlenecks of autoregressive inference in transformer-based language models. I won't be going into too much depth, such as multi-GPU or multi-node scenarios. It's a simple single GPU scenario. And then I want to explain how our unique hierarchical architecture mitigates these kind of bottlenecks to achieve a 10 to 20x increase in batch throughput compared to vanilla transformers. So the contents of the talk will be divided into 4 parts. First, I'll give a visual overview of the key challenges, so the bottlenecks that I mentioned and how our architecture solves them. And then in the later sections, I'll go into architectural details, detailed results and analysis, and discussion and future works. So let me start with the visual overview. So the challenge of transformer-based language models, the autoregressive ones that we use in like ChatGPT or those popular models, is due to self-attention. And so self-attention is the root cause of the inference bottlenecks that we will deal with in our paper or in this talk. So let me just explain the inference costs due to self-attention. So I want to give this explanation using some visual cues. So here, each row represents a single transformer layer. Each box represents a hidden state, and each letter here represents a subword token. So these are all input tokens, and each column basically represents one token. So there are 2 stages to inference in autoregressive transformers. So first one is when you give like a long prompt to say ChatGPT, it has to process all of the information in that prompt, and that is what we call the prefill stage. Now, in self-attention, we have to attend to all of the what we call KV states in every layer using self-attention to decode the next tokens. And so we have to fill this KV cache for all the input tokens. That means that for all the input tokens, we have to forward them through the entire transformer so that we can obtain these KV cache values. And so that's the prefill stage. And that is why it takes quite some time for you to see the first token when you use services like ChatGPT. And then also another cost is that you have to keep the KV cache of the entire prompt within your GPU memory during your entire inference stage. And that could be very big because prompts can get very, very large. Now, the second stage of inference is what we call the decode stage, where the contents of the output tokens are generated one by one. Now, the key bottleneck here is that while we have to compute just the final column that we see here, so we have to compute tokens one by one, what happens is we have to actually load the entire model parameters from the GPU memory, what we call the HBM memory, from into the compute units every time we decode a single token. So for each token, we have to load the entire model parameters, which is a huge memory bottleneck. And also we have to retrieve all of the KV cache from previous tokens so that we can apply self-attention. And so these 2 things causes a major memory bottleneck, which is why the compute units, so KV cache retrieval is a huge cost. And that's why during the decode stage, the compute units of your GPU are actually not doing much because it's waiting for all that memory to be fetched from the hardware memory. And we Yeah, so we explain these key costs in the updated version of our paper, in the main paper. So you can check that out for details. But basically, yes, the key bottlenecks, especially in batch inference for autoregressive transformers, is this KV cache prefill latency for the prompt, for processing the prompt and storing that KV cache, which can be very big, and also retrieving the entire KV cache for every decoding step. Okay. So then how do we cut the costs of self-attention? Well, we want to focus on what aspects of self-attention makes it so expensive in the first place. So the reason why the aforementioned bottlenecks are so high is because self-attention, or I guess transformers in general, work with very fine-grained input units. So they work with subword tokens, which are, well, compared to, I guess, how humans think, they are very, very small input units of input or content. And also, all transformers use a global window. So they apply self-attention to the entire previous context. Some recent papers, starting with, I believe, sorry, I can't remember the exact architecture. So some architectures have started to use local sliding window attention in their model architecture to mitigate some of these costs. But they don't apply it to all the layers. And also they actually use a window of like 2,000 or 8,000 tokens, which is still quite a lot of tokens to keep in memory and retrieve from the KV cache. So yeah, to summarize, the fine-grained units and the global application of self-attention is what makes the bottlenecks I mentioned very expensive. And also, and actually this global aspect can be a very huge cost factor because we don't know how many tokens that we want to deal with. So previously, the context length of transformers started with like 500 or 2,000 tokens. Now we have models like Gemini that can work with 1 million or 2 million tokens. If those use standard transformer architectures, then basically we have the self-attention bottlenecks. So the KV cache retrieval bottlenecks is exacerbated by the need to retrieve the cache for like 2 million tokens, which I guess will have a lot of memory costs. Okay, so the global and fine-grained aspects are what makes self-attention so expensive. So that is our analysis of the challenges of the autoregressive inference bottlenecks. And so our solution is to build a hierarchical architecture that mitigates some of these costs. So I'll just visually go through what our architecture is and explain how those bottlenecks are relieved. So this is just how a vanilla transformer would decode the next token given the tokens A through L. So again, we have to prefill, store, and retrieve the KV cache of all the input tokens in the vanilla transformer. In the case of the block transformer, we can divide it into two parts. So in the lower layers, what we do is we try to capture the global context because it can see all of the input tokens. And so to do that efficiently, we apply coarse-grained processing. So what we do is instead of working at the individual token level, we take groups of tokens. In our paper, we use groups of 4 tokens and use a lightweight embedder to embed them into a single, what we call a block embedding. And then the lower layers, or what we call the block decoder part, processes these inputs in terms of block level inputs rather than token. So we go from fine-grained to coarse-grained processing, and that makes the global processing a lot faster and lightweight. In the upper layers, we want to return to the level of fine-grained tokens because we want the outputs to be in the level of tokens. But instead of applying global attention, we apply local attention. So what that means is attention is only applied within each individual block. And so instead of seeing up to all the previous tokens, which can go up to like 2 million, the token decoder sees up to the 4 or 3 previous tokens within the current block during their decode stage. And notice that, so let's say in this scenario where we want to decode the next letter M from given the inputs A through L, well, you can see that the token decoder only attends to these tokens, and so it never actually has to see the tokens that come before. And so we can simply remove them from memory. And also what that means is we did not have to prefill these tokens in the first place during the prefill stage. So that saves a lot of time during the prefill stage. So what happens is actually in the prefill stage, you have to process all of the input tokens in the block decoder, but we only do that in this coarse-grained block level. So that kind of removes the computational overhead. And then in the upper layers, we just don't have to, we can skip most of the prompt tokens during the prefill stage. So it becomes a very lightweight operation. And then for generation, we only have to autoregressively process the next tokens within the token decoder or the upper layers. And that is our block transformer. And so during the decode stage, what happens is, given these inputs, we output the block embedding from the block decoder, and then we obtain the next tokens one by one. And you notice that, again, we only have to apply attention to tokens within the local block, and therefore we don't have to store or retrieve all of the previous KV cache at every generation stage. So that also makes it incredibly fast. And also it relieves the memory bottleneck from KV cache. So the GPU compute units are able to do more work. And so we call that, like we say that the model flop utilization becomes much higher. So this is how we relieve the cost factors of autoregressive inference bottlenecks. In the lower layers, we remove the fine-grained aspect, and in the upper layers, we remove the global aspect. And so we use a hierarchical architecture that goes from a global coarse-grained processing to, in the upper layers, local fine-grained processing. And that's how we mitigate the bottlenecks kind of uniquely in each section. And so what's the verdict? Well, there's bad news and good news. I'll start with the bad news. Compared to vanilla transformers, we actually require 2 to 3 more parameters to match the performance using block transformers. And that's because we have added all of these kind of limitations to the architecture. The good news is that our block transformers can achieve, especially in batch processing scenarios, we can achieve 10 times batch throughput. And of course, this is at the same performance, so using 2 or 3 times more parameters, and of course on the same hardware. So we think this is very beneficial for scenarios such as very large cloud deployments where you would use a large batch size, and the model parameters are not really relevant. As long as you can fit the model parameters in your servers. Of course, this would not be very beneficial for like local inference where it's hard to fit the model within the device itself. Yeah. So that is an overview of the challenges and how we solve them using block transformers. Now, let me try to quickly go through all of the details of the architecture and our results. So this is the architecture figure that we use in our paper, and I'll go through each of them, each of the components in the architecture. Well, first of all, I think the visual overview kind of showed that so how the forward operation and how the generation happens in the block transformer, but I'll go over them once again. So let's say, for example, the inputs A through L are given over here. Then the 3 input blocks, so these are 12 tokens. They will be embedded into 3 blocks, each having 4 tokens inside them. And so the embedder embeds 3 input blocks based on these tokens. And then, And then the block decoder takes these 3 input blocks and decodes the output block from the last position. And we call this the context embedding because it contains the context relevant to decoding the next block. And we're talking about the context of the previous tokens, A through L. And then next, the token decoder takes this single context embedding as relevant context information and tries to autoregressively decode the tokens in the next block, M, N, O, and P. And by autoregressive, I mean that in the first step, it takes this input, outputs m. In the next step, it inputs m, outputs n, and so on. So, I mean, like one by one. And for the overall other architectural details that goes into transformers, we adopt those from Pythia, which was a popular open source model, which was quite recent at the time of development. Of course, now we have a lot more popular open source models. And for some embedding dimensions, I guess I should mention that in Pythia or regular transformers, the model dimension is typically the same as the input dimension. That means the dimension of the input token embeddings. And so we have the input embedding table, which is a matrix of vocab size times the dimension. And the classifier for the token outputs is the dimension times the vocab size again. So that's your typical transformer. Next, I will go through each component in our block transformer based on that vocabulary. So in the case of our block transformer, each input token is embedded using the embedding table for the embedder. And we embed each token into dimension size that is 1/4 of the default model dimension. And then we concatenate the embeddings of these 4 input tokens into a single block embedding, and that makes the dimension to go back to D. And that's how we embed our block embedding for each input block. So it's very simple. There's no additional processing going on here. Some alternatives for the embedder design is that we could use some sort of encoder style transformer. So that means taking in the input, taking in 4 input tokens and applying a transformer to try to, I guess, enhance the understanding of that given block. Right, and then from the output of that encoder style transformer, we can, again, concatenate the outputs, or we can use a BERT style CLS token, which will contain the information of that block. So that's just an alternative design that we can consider. The block transformer is fairly simple. It's a standard transformer layer with model dimension D. So it's practically just some layers that we take from Pythia. And then in here, each input unit, so what used to be a token in this transformer now represents a block that has been embedded by the previous component. Next is the token decoder. So again, this is a standard transformer, or these are transformer layers, similar to standard transformer layers with, again, the same model dimension D. And so in this case, we actually have to add another embedding table just for this component. And so we have another embedding table. In this case, we operate at the level of tokens. So the embedding dimension is just D. And then the token decoder takes in the context block embedding, or the output block embedding of the block decoder. And then it uses it as a prefix token to extract the information from that embedding to then autoregressively decode the next block of tokens. And so after M is generated, we put it back into the model, and that token is embedded using the token decoder's independent embedding table, and so on. And again, there are alternative ways to take in the context embedding that came from the block decoder into the token decoder. So we can project the output embedding into multiple tokens and then sum them with the existing input token embeddings. We can also apply some sort of cross attention. So while these tokens are being decoded, we can apply cross attention to some projected version of the context embeddings from the block decoder. Yeah, so I'll just give some time for that to seep in. It's a bit complicated at this stage. Okay, next, I want to give some details about the token decoder. So I mentioned that, okay, let's look at the previous. So I mentioned that the output from the block decoder is used in the token decoder through this as a prefix token. although we don't have to use one prefix token. So what we do instead is we project the context block embedding from the block decoder into multiple prefix tokens. And what happens is then you can, because this information is kind of dispersed across multiple tokens, I guess, then self-attention can better attend to this information while it is decoding the next tokens. And also this enables the model to allocate additional computation to the context part. And we believe this would have a similar effect of pause tokens, which kind of got the attention of lots of folks in model architectures. And we note that this barely affects the actual inference generation time, because as I mentioned, because of the reduction in KV cache memory retrieval in the token decoder, the model or the GPU is much better able to utilize its compute units. So even if we give or apply more computation to this step, the GPU can process it very fast. And so we refer to the number of prefix tokens, so how many tokens we projected this information into, as the prefix length. As for the dimension and layer allocation for the block decoder and the token decoder, well, as I mentioned, the dimension size is the same across block and token decoder. This might actually be kind of questionable, because the block decoder, each input unit represents 4 tokens, whereas the token decoder tokens represent one subword token. And so you might think maybe it's better to apply like a bigger dimension size to the block decoder. We ran some preliminary analysis on this, and we found out that whatever these tokens actually represent, it's actually beneficial to follow the layer number to dimension ratio across both of these components. And also, we found that it's actually optimal to allocate the same number of layers to the block decoder and the token decoder. And so because excluding the embedding and output classification parts, this is actually the exact same architecture as Pythia, just cut into half and then giving some different roles for the bottom layers and the top layer. And so this actually makes it very easy for us to adapt the model and the parameters from an existing vanilla transformer like Pythia into a block transformer. And we'll explain how we did that in the later results. Yeah. Okay, so we did all of that. Let's see how well our model works, and I'll also provide some analysis on like the individual components that I just mentioned. I'll start with main experimental results. So how we compared this architecture to just the vanilla transformer architecture is we pre-trained both of them from scratch using the same settings. So using the same, the pile pre-training data up to 300 billion tokens, using Pythia with up to 1.4 billion parameters as the base architecture. Note that Pythia uses multi-head attention. And some of you who know like KV cache bottlenecks probably know that recent models don't use multi-head attention. They use things like group query attention, or recently DeepSeek announced multi-head latent attention, which actually kind of orthogonal to the block transformer. It reduces the KV cache intensity, or the amount of KV cache compared to the size of the model. So that's one thing that is a caveat in our results. But basically, we compared with the same settings in our paper. For evaluation, we evaluated perplexity on the training set, because all the tokens in the training set are new for the model, because we only use one epoch, and also some standard zero-shot evaluation tasks used for these small models using the Hugging Face evaluation harness. For speed measurements, we measure the batch throughput under the maximum batch size allowed by a single H100 GPU. We consider two settings: a prefill heavy setting, where you would have a long prompt and a short generation, and then a decode heavy setting, where with a small prompt and a long long generation. Now, we think that the number of tokens for prompt and decoding will increase in the future because as you try to put more context information in the prompt, or techniques like retrieval augmented generation retrieves a bunch of documents to put into the prompt. And possibly, my guess is that we'll try to put more context on the individual user into the prompt as well. So this will probably increase. And for decode heavy settings, we know that companies are working on thinking models, which generate a bunch of tokens to improve their outputs. And so probably the number of output tokens will increase as well, which will actually give more benefit to our the cost savings from block transformer. But yeah, let's get into the main results using these standard settings of today. So just to give you a summary of main results, as mentioned before, the performance kind of forms a parity around. So for the vanilla 160 million parameter Pythia model, we have to use a block transformer with 420 million parameters to get similar performance in terms of perplexity and zero-shot evaluation. And also for 400 million, we need roughly 1.1 or 1.4 billion parameters to get similar performance. And comparing these models with similar performance, the block transformer achieves a 2 to 20 times batch throughput, as you can see in these graphs. We also consider longer prompt lengths with 8K and 16K tokens, and the difference is maintained throughout those settings. And we also find that the perplexity, so the loss, and the zero-shot task evaluation performance are roughly correlated to each other. Okay. We did a lot of ablations and analysis on our architecture. So as I mentioned, we allocated the layers to the block decoder and token decoder. So the bottom and top half parts, we allocated layers 1 to 1. And we found that this is actually optimal regardless of the model size, which was interesting to us, which is a good news because you don't have to tune this parameter for every model size. And also we found like a U-shaped perplexity curve across settings. So using 1 to 2 or 2 to 1, you get a similar perplexity and so on. Also, we measured the perplexity of the predictions from the token decoder depending on which position it came from within the block. So if that changes too much, then that might not be good news because your outputs might be very sporadic based on which position it was in after dividing by 4 or modulo 4. And interestingly, we found this kind of U-shaped curve. We believe this is because as the position gets higher, basically you need to, well, the context information given by the block decoder might not be enough to decode blocks way into the future. And so there's that kind of an effect. And also the opposite effect is in the token decoder, as the position increases, you can see more of the actual tokens within the context. And so that will have an opposite effect of lowering the perplexity as you go forward. That's the same as vanilla transformers where, as you increase the token position, the loss generally starts to go down. So there are these kind of two effects that are applied together, and that's why we believe there's a U-shaped perplexity curve. We also apply ablation on the block length. So we, in our previous explanation, we said that each block is a representation of 4 input tokens or subword tokens. We also consider 2, 8, and 2 and 8. We find that with a larger block length, the loss generally increases, so the performance drops. I think this is obvious because as the block length increases, the block decoder basically gets weaker and weaker. So it's a much more, it gets more coarse. So that as you apply more coarse processing, we think obviously it uses less computation, therefore loss will increase and performance will decrease. But at the same time, because of that, we believe we find that the batch throughput increases significantly. And also, as we apply larger block length, the optimal parameter or layer allocation shows that a larger token decoder is beneficial, probably because each layer in the block decoder becomes weaker as we use a larger block size. And we also observe similar U-shaped curves and some different perplexity curves as the length goes too small. Also, we apply ablations on the component design. As I mentioned, there are many ways we can design the embedder and the token decoder. We found that the optimal is what we used, basically a lookup table and then concatenation for the block embedding, and then taking the outputs from the block decoder using a prefix style token decoder. You can see the perplexity for other approaches. Also remember the prefix length, which is how many prefix tokens do we project for the context embedding, so for the token decoder. And as we use a larger prefix length or more prefix tokens, it increases performance because obviously we're applying more computation. And we see that this kind of plateaus around 4 prefix tokens, although we used 2 just as a middle ground between performance and some training overhead that is added due to prefix tokens. Next, long context performance. You might think that because we kind of weaken the global processing power of self-attention in block transformers, the long context performance might suffer. Now, we find that block transformers can handle long context based on 2 points of evidence. So first, we see that the perplexity drops as you give more context tokens to the model, similar to vanilla transformers. We validate this up to 8 tokens in some further analysis. And also we apply the needle in the haystack tests, which come out a lot in architecture studies. And we find that the block transformer can perfectly retrieve needles within the context up to 8 tokens, regardless of the position. Now, an important thing to mention is that needle in the haystack probably is not the best or a complete evaluation of long context performance, because all you have to do is just find a number from the previous context. We think that in terms of actual long context performance, so when there's a lot of information in the context and you have to do some kind of processing based on that context, perhaps it's possible that the block transformer can perform a bit worse than similarly performant vanilla transformers. So some study is required for this as well. In terms of training cost, I mentioned a lot about how the block transformer mitigates inference bottlenecks from transformers, but the training bottlenecks are pretty much the same. So training cost is roughly correlated with the number of parameters. And as we said, we need more parameters to perform same as vanilla transformers. So we actually have to apply more flops in that regard. However, if you want to achieve the same output throughput, then the story becomes kind of different. So this is related to the scaling law and the llama architecture. So in the scaling law, the typical model scaling law shows that if you want to optimize for your training budget, then you should, for a certain model size, you should train up to a certain number of tokens. That's the optimal. But what recent models do is they train much further past this optimal point that started with the llama architecture, because we don't want to optimize just training costs, but the inference cost. So for the same model size and for the same inference cost, you want to get the model performance as good as possible. And so they train way over the optimal point. And so the point is that current models try to optimize inference cost by applying a lot of training costs into their models. And so we compare these two architectures from that light. So for the same throughput, for achieving the same throughput and using the same amount of training cost, how do these architectures compare? And we find that block transformers outperform vanilla transformers when you do this for the same throughput. So for same training and inference costs, we can say that block transformers actually offer an advantage. Yeah. Okay, so that is the end of our results and analysis. I just want to mention a couple of discussion points and some future works that perhaps we could discuss during the Q&A session. Okay, yeah, so for uptraining schemes, I mentioned that you can take a pre-trained vanilla Pythia model and then uptrain that into a block transformer. We actually did some preliminary experiments on this, and we find that if you use 20% of the existing pre-training budget using an existing pre-trained vanilla model, then you can achieve the same performance as pre-training from scratch with the entire budget. So that gives some potential on uptraining methodologies. Also, we want to consider increasing the flop density of the block decoder. This means that right now the block decoder applies coarse-grained processing. And this means that compared to a vanilla transformer, it uses the same number of parameters, but it applies 1/4 of the computation in terms of flops. And so if we increase the flop density back to the default while preserving the attention cost benefits of this architecture, then it might be possible to kind of relieve the parameter requirements of the block transformer. So we can make, instead of using 2 to 3 times more parameters, based on our results, we think we can use like a 1 to 1.5x amount of parameters, and that should make the throughput benefits even better for our architecture. So that's some feature work that we can consider. And there's many of these kind of knobs that we can turn in the architecture. So like block length, flop density. There's also how much attention should be applied to the token decoder. So instead of applying attention just within a single block, we can expand attention to some previous blocks just to relieve that locality just a bit. And yeah, there's many parameters that we can tune to give different insights from this model. And also, I think this architecture kind of shows the potential for what I call weak global to strong local architectures. Because as I mentioned, previous transformers have a lot of attention inference bottleneck because attention is applied globally, fine-grained. But if we loosen either one of these constraints, then we can make the inference bottleneck go away substantially. And so by doing that kind of approach in architectures, we can significantly make the inference faster. And I think this is just one example of how you can achieve that. But I'm sure if we try to focus on this aspect from scratch, then it might be possible to come up with better architectures that can optimize this use case. Because this, our architecture was actually kind of coincidental. The benefits from autoregressive inference were actually discovered after some initial experiments, but that's another talk. So yeah, I'll leave you with this for the discussions. And so that's the end of my prepared slides, and I'll just end you with this. So Einstein once said that if you have an hour to solve a problem, you should spend most of the time thinking about what the problem actually is. And so we think that by doing so in the block transformer and focusing on the real bottlenecks of autoregressive inference, not just training flops or parameter size, we were able to make this model 10 times faster in certain scenarios. Yeah, so that's the end of my talk, and I'll open it up to questions. Oh, sorry, I didn't check any of the chats during my presentation. I had a different screen open. Sorry about that. Yes. Bavnik, is that how you pronounce your name? Yes, the Mistral models were the first to apply sliding window attention to like modern transformers. Mm, yes. Oh, sorry. GPT-3 started using sliding window attention kind of in the back and forth. So they use global, local, global, local attention. And then Mistral models kind of revived that for open source models, to the best of my knowledge. Yes, Bhavnik mentioned that we can apply adding more context tokens during the token decoding part. I think that was kind of covered with the number of prefix tokens. So here we use the output context embedding from the block decoder. Basically, this contains all the information that is relevant from the previous context in decoding the next block of tokens. And one way to relieve the bottleneck, information bottleneck here, is to project it back into these, into multiple tokens. Of course, the bottleneck happens here, where we try to keep all of the information in a single embedding. Now, there's many ways we can relieve this. So one way would be in the final layer, we could actually expand this back into multiple tokens so that it can attend to the previous context and actually get more information to fit into the larger space. I also discussed at the end of the discussion, instead of allowing the token decoder to just apply attention in here, we can expand the attention window to 2 or 3 or more blocks to relieve that that bottleneck. So there are many ways that we can consider. Okay. Yes, and of course the first model to so by Barabbas, the first model to, or the first papers to announce or experiment with local attention or sparse attention were models like longformer, sparse transformers, and many others that you can check for references in our paper. Okay. Yeah, feel free to leave any additional questions.
Hi. I was curious about your alternative input methods that you suggested.
Mm-hmm.
So you mentioned that one of the core reasons why we have block decoder is because we want to save on KV retrieval, KV cache memory and retrieval.
Mm-hmm.
So if we have I'm not exactly in the core KV cache research, so I'm not exactly sure. But if you have KV cache for all the block decoders and you're doing coarse-grained, then memory would already be saved, and only retrieval part would be affected if you have more context block tokens when you're doing token decoding, right?
Yes. So you mean that increasing the let's say
the context tokens, increasing the number of, I'm not sure what to call them, the tokens that come out of the block decoder.
I believe it's the prefix tokens.
Prefix tokens are projected from that one block token, right?
Yeah. So you mean the actual, so within the block decoder,
right?
The last,
so,
yeah.
My question is, how does it scale when you increase the number of block tokens that the token decoder would receive? Is that something you've explored before?
Oh, so do you mean, say, we can use maybe multiple recent outputs from the block decoder?
Right.
I see. Oh, yes, that's another way to solve the bottleneck, and no, we haven't actually considered that approach in the paper. Yeah.
I see. Is that something that you think would be beneficial, like in terms of like KV retrieval?
Absolutely. So there would be almost zero additional bottleneck in terms of computation or KV cache retrieval by by doing that. Same goes for applying attention to some more previous blocks, because we're increasing the number of tokens for the KV cache from like 4 to 8 or 12, which is not much compared to like the full context. And so, yeah, both of those approaches would not increase the cost and would probably revive a lot of the performance loss that we get. In the discussion of the paper, we mentioned that we want to kind of test the most extreme version of this idea just to see how the potential, and obviously all these methods that you mentioned can actually improve the performance.
I see. Thank you so much.
Yeah, thank you.
Hi, thank you for the great presentation. I have some question. So I think so in your architecture, actually, lower layers are working on some kind of long context things, and yeah, for upper layers, these are local. So I mean, but for standard transformer, if you analyze I mean, attention patterns, something like that, then we can see that even in upper layers, they are doing some long range interaction. So, I mean, I don't know, maybe if we enforce them to, maybe in the pre-training stage, if we enforce them to only use lower layer, I mean, only use low layer for long range, will it be, I mean, how can I say? So why the standard transformers are learned to do long range in all layers? Do you have any insights on that? Yeah.
Well, based on experience, like looking at all the training curves and perplexity during our experiments, the intuition that I gained, which should be fairly obvious actually, if you think from like first principles, is that when you have an architecture and you apply simple gradient descent throughout just all the layers, then I think what happens is the model tries to utilize whatever computation or whatever like connections that the model has to maximize the performance. So because in vanilla transformers, we give the opportunity for the model to attend to all the previous tokens in any layer, it will try to use those as much as possible. And so even if it's not too, I guess, efficient, or even if the effect is minimal, it will try to use all the attention in the upper layers. Although intuitively, I guess I believe that the requirement for attention could be less in upper layers, and just if you retrieve the information from the lower layers, then the upper layers can try to just try to process the information in upper layers without having to attend to all the previous tokens. To verify this, you could apply smaller windows of attention in standard transformers and see how much the performance drops. Then you will see how important they were. But obviously, I think for meaningful comparison, or for like to give a perfect picture, you would need to test on a very large model like 7 billion. That way you can test on actual tasks where we can see the actual performance, like GSMAK or those kind of things, not the simple evaluations that we applied in our paper based on perplexity. One intuition or one thought that I had for why we can probably apply attention just in the lower layers or kind of in a weak way is that basically when we want to do some long context processing, so let's consider a long context benchmark where you have a lot of information and then a question is given in the recent context. Basically, the model still has to retrieve the information from the previous context, and then it will have to do some additional processing on that information because the question has only been given recently. So you can't really think about all the possible conclusions that you can make from the input tokens in the prior like KV cache. It's hard. You can't store that information here. You can only start thinking about the given question after it has been given. And therefore, I think would be intuitively, you would need to first retrieve the information, just retrieve the raw information. Then that could be happening in lower layers. And then for like actually answering the question based on that information, you would have to do it locally anyway. So I think that's kind of the intuition for why this kind of approach would be not like best performance, but like can do most of the work.
Makes sense. So I think that, yeah, thank you for the great answer. And also could be also then related to the KB cache compression. I mean, so in the, maybe if we want to compress, maybe then in the upper layer, maybe if it focus more on the local, if that's fine, then we can only, I mean, maintain those KB caches, right?
Yeah, I think so.
Yeah.
I think just like a small comment, I think a lot of the limitations with existing KV cache compression is that they kind of evaluate on like single query situations. So you give a specific query, and then they start to compress the information. And so what happens is it can kind of overfit to that query itself. And more recent benchmarks like SC Bench, so that's SC Bench that I saw at NeurIPS this year, is that they evaluate those methods on multi-query situations. So after the KV cache has been compressed, we give it a new question, and we see that a lot of the performance actually drops because it compressed overfitting to that question. And so I think some more work has to happen here. And I think like offloading to, let's say, CPU memory, that is obviously a good approach because you can always retrieve that information later. Yeah, and also I guess what the block transformer does is it kind of compresses or kind of stores just the raw information within the block decoder, and then we can retrieve it with the coarse attention and kind of do more processing in the token decoders. I think that's what could happen in our block decoder, in our block transformer.
Yeah, thank you. And also, I mean, you empirically show that, I mean, having the same number for block decoder and token decoder is, I mean, optimal. But do you have any insight or intuition online?
I think it's there's a trade-off between these two components because they clearly have their strengths and their weaknesses. In block decoder, you can apply attention globally, while the number of flops or the computation intensity is a lot lower than token decoder for the given amount of parameters or layers, whereas in the token decoder, you can apply more computation, but with less attention. And so I think as you change the constraints of each component, so let's say if we increase the attention span of token decoder bigger, then it becomes stronger compared to the number of layers. Therefore, it will be more optimal to give more layers to the token decoder. If you make the block decoder stronger by, let's say, decreasing the block length to like 2, then it will become less coarse. Then that's why the block decoder, it's optimal to give a bigger number to the block decoder. So it's just a matter of that trade-off. And we think the 1-to-1 ratio for block length of 4 was just coincidental. Just the trade-off happened to be at 1-to-1. So it looked like a nice number, but I think that's what happened.
And also, yeah, I think it reminds me something like, I mean, it's also related to some kind of tokenization, because yeah, it's kind of, I mean, having some, okay, I don't exactly remember, but maybe in earlier work, maybe it first start from very fine-grained, maybe byte level tokens, and then it gradually, I don't know, it somehow merged into some tokens, and then it processes. So do you have any
actually, so there's two lines of related work. One is what you mentioned, which is actually has been done in what is called the megabyte architecture that came into this work. And actually it has almost the same architecture overall. Like the details are different, but it actually does have like a very similar architecture. So there's that, and there's also recent models like large concept models, which actually tries to, it starts with subword tokens, but it embeds or groups the input based on concepts. It actually does a adaptive length grouping in their case, and then like the core model does the decoding in terms of like the large concepts. And that's actually what we first tried to aim for in our paper. But then while simplifying, yes, thank you for the reference. While simplifying, we gone to an architecture more like megabyte, where the number of tokens is fixed. But we wanted to use token level inputs just so that it's easier to adapt from existing vanilla transformers, the popular transformers. And also, what is not shown or what is not investigated in works like Megabyte is that these kind of inference time bottlenecks due to attention were not really considered as a cost factor. And so in their case, what they do is they use a very small embedder, very similar to ours, and also a very small token decoder. And so the whole idea is that the actual processing of information is happening in the middle layers at the group level, and these are just they just kind of map the representations back and forth. However, that is completely different from what I believe is happening in our architecture. We think that block decoder is more of like a context compressor, adaptive context compressor, and then token decoder is actually doing a lot of the heavy lifting. And so that is why under like same parameter constraints, it's optimal to do a one-to-one allocation, and so have a much significant local model. Whereas in Megabyte, they also did a optimal allocation experiment. In their case, they optimized for flops. So obviously, token decoder uses a lot more flops compared to the number of layers. So doing the same analysis, but with the flop cost comparison, they conclude that the token decoder, or the local model is what they call it, to be a lot smaller. And that's how they interpreted their model. Whereas we focus on inference bottlenecks, and the token decoder has much better MFU, like compute utilization. So the flops are a lot, but it actually takes a lot less time. If you optimize from that perspective, these are the conclusions that you come out with. And I think that is worthy of another paper, personally. Yeah.
Thank you. Thank you so much.
Okay, thank you for your questions.
Thank you so much, Namgyu, for the session.
Okay, all right. Thank you for inviting me, and thank you, everyone.